Thank you for the introduction. Hello, everyone. My name is Kang, a postdoc researcher at Richard Institute. And in this talk, I'm going to present a part of my thesis work at the University of Illinois at Urbana-Champaign, working with Professor David Kale and Professor Andrew Schleif. The title of the talk is The Magnetic Property and Energy Dispersion of Metallic Antiferromagnets. And this project is supported by the Illinois MERSEC. So we are interested in materials for magnetic memory device. Ferromagnets have been widely exploited to store the binary information using its magnetic orders. So up and down spins of the ferromagnets corresponds to the 0 and 1 binary information. The most popular magnetic storage example is the hard disk drive. So first invention was done by IBM. It was like 5 megabytes storage with the human size volume in 1956. About 7 years later, it became 20 terabytes within our hand, which has the 4 million times larger storage nowadays. However, the ferromagnetic device has started to face their limitations. For example, its spin frequency is limited by the gigahertz, and the data compactness is limited by the stray field. So meanwhile, in 2016, electrical switching of antiferromagnets is first demonstrated. Unlike the ferromagnets, antiferromagnets has this antiparallel spin configuration. Thus, using this 90-degree rotational difference can be used to store the binary information like 0 and 1. So this research triggered the further investigation on the metallic antiferromagnets. Antiferromagnets have strong advantages for magnetic memory device. First, the stray field generated from the ferromagnets is emitted outside of the materials, which can affect the nearby materials. And this feature seriously reduces the storage compactness. But antiferromagnets does not generate any stray field due to the absence of non-magnetization, enabling more compact data storage. Second, about the spin dynamical response. Against the external stimulations, antiferromagnets can show the spin dynamics with the terahertz frequencies, which is 1,000 times faster than the ferromagnet does. Lastly, the behavior against the magnetic field. So ferromagnets are sensitive to external magnetic field, so it is easy to manipulate the magnetic order using this external field, but also easy to affect the field. For example, the magnetic strip on our credit card should be protected from magnets. On the other hand, antiferromagnets are relatively robust against the external field, so it is easy to protect the information we save, but it is not easy to manipulate the magnetic order at the same time. So that's why the electrical reading and the writing of metallic antiferromagnets are so important. So the overarching problem of metallic antiferromagnet studies are three. So quantification, visualization, and characterization. So first, quantification of magnetic interaction. Magnetic phenomena are generated from the merged magnetic interactions. So thus, to understand the magnetic phenomena, it is important to quantify the exchange interactions and the magnetocrystalline anisotropy energy in atomistic scale. Next, the visualization of atomistic magnetic structure under stimulations. For example, when magnetic field is applied, then we can measure the macroscopic properties like magnetic susceptibility, but we cannot know what happens in atomistic scale, which prevents the deeper understanding of magnetic phenomena. Lastly, characterization of metallic antiferromagnets. Due to the absence of the non-magnetization, conventional characterization tools are mostly unavailable, thus it is important to find another way to characterize the antiferromagnetic features. In conclusion, these overarching problems prevent the discovery of new metallic antiferromagnets with better performance. So I believe the first principle method might provide a solution for these problems. So the goal of this project is to investigate the ground state metallic antiferromagnets to understand their magnetic phenomena using first principle methods. So in this project, the magnetic interactions are quantified as the exchange interactions and the magnetocrystalline anisotropy. So exchange interaction can explain the magnetic configurations, while magnetocrystalline anisotropy can answer the equilibrium orientation of the entire magnetic structures. Furthermore, we can extract the energy dispersion of metallic antiferromagnets to identify the contributions from the electron, boson, and magnons. This result can be utilized to understand the excited state properties, such as the estimation of this magnetic debase speed, or heat capacity, Néel temperature, and the magneto-optics from the metallic antiferromagnets. So let's start with the fundamental magnetic interactions. So exchange interactions explain how two different spins are energetically aligned. A key quantity is an exchange coefficient. So when the coefficient is the positive, then two spins prefer to be parallel or ferromagnetically coupled. And when it's the negative, then it become anti-parallel or antiferromagnetically coupled. So once we can calculate the exchange coefficient, we can explain the ground state magnetic configuration. And moreover, we can estimate the magnetic susceptibility and the Néel temperature. So here I brought an example, antiferromagnetic iron to arsenide. So this material has a unique magnetic configuration. So when we see it along the p-axis, you may realize that it has 3 consecutive spin layers with alternative spin directions. And it has also 2 different magnetic sites. So it's M1 and M2 have a different magnitude of magnetic moments. Sorry for interrupt. From spin polarized relativistic Kringle-Kohn-Rockström method, we can extract the exchange coefficient of antiferromagnetic iron to arsenide. Z1 is the first neighboring exchange coefficient, so showing the M1 interactions. Since this J1 is the positive, so it explains the in-plane ferromagnetically coupled M1 layer along the AB plane. Next is second neighboring exchange coefficient, J2, is the M1 and 2 interaction with the positive numbers. So it explains the ferromagnetic coupling of the M1 M2 layer, resulting in the 3 consecutive parallel spin layers. Lastly, the third neighboring exchange coefficient, J3, is the M2-M2 interaction with the negative value. Due to this negativity, entire 3 consecutive spin layers are flipped. So even though the magnitude of J3 interaction is small, the sign of the J3 is a key factor that determines the antiferromagnetic configuration of entire iron to arsenide structure. So from the calculated exchange coefficient, we now know the magnetic configuration of iron to arsenide, but we still don't know which direction the entire magnetic structure orients. That's determined by magnetocrystalline anisotropy energy. So here are some examples. So with the antiferromagnetic configuration determined by the exchange coefficient, it can orient along the C-axis, A-axis, or 110 direction. So any direction can be possible. But the equilibrium orientation is determined by this magnetocrystalline anisotropy energy, which is the energy change with the Néel vector directions in terms of the 2 spherical coordinating angle. Magnetocrystalline anisotropy energy has been widely studied for a long time, and it can be characterized by the crystallographic symmetry. So tetragonal structure has an outer plane anisotropy along the AC plane and the in-plane anisotropy along the AB plane. In more details for the magnetocrystalline anisotropy, there are 2 major contributions. First one is the spin-orbit interaction. So originate from the spin-orbit coupling effect. So it can be obtained from the density function theory calculation. And another contribution comes from the magnetic dipole-dipole interactions. So each spins emits the stray field outside the moment and which interacts with the other spins. So, but this effect is not included in DFT results. So we introduced the classical approach to calculate it using DFT ground state magnetic structure. Then here's are the magnetocrystalline anisotropy results of the antiferromagnetic iron to arsenide. So first, we check the AC plane first. So as the Néel temperature changes away from the C axis, then total energy goes down, and it becomes the lowest energy when they orient along the AB plane. So both the spin-off interaction and magnetic dipole-dipole interaction shows a twofold symmetry. So we can determine that it prefers the easy plane magnetism. One unique point is that the MDD contribution is about the half of the spin-off interaction in this case, and thus the MDD contribution shouldn't be neglected for accurate magnetocrystalline anisotropy energy estimation. Now here is the in-plane anisotropy scanning with the AB plane. So due to the four-fold symmetry of the crystal structure of iron to arsenide, MDD contribution is canceled out, and only the spin-off interaction contributes to in-plane anisotropy. So it shows a four-fold symmetry, which means that there are two lowest energy direction along the 100 direction and the 010 direction, and thus we can use the iron to arsenide as an antiferromagnetic memory device using 90-degree difference, rotational difference of Néel vector in AB plane. And calculating in-plane anisotropy coefficient, K22, is quite close to the measured value, although it is the very small energy barrier, which is close to the DFT accuracy limit. And in conclusions, iron to arsenide have 3 spin layers with the antiferromagnetic configuration orienting along the 100 or the 010 direction from all the magnetic interaction calculations. Now we know the magnetic structure. The next quantity we want to know is the energy dispersion of metallic antiferromagnets, which can explain their properties and energetics with excitations. Antiferromagnets consist of the 3 quasiparticles: electron, phonon, and magnon. An electronic band structure can be obtained from the Quantification eigenvalues from DFT calculation. And phonon is quantized lattice wave in materials, and its dispersion relation can be calculated by the finite displacement method in DFT. And lastly, magnon is quite similar to the phonons. So it's quantized spin wave in magnetic materials. So its dispersion can be extracted from the linear spin wave theory using previously calculated exchange interactions and magnetocrystalline anisotropy energy. So here are some examples for the calculated quasiparticle energy dispersion of antiferromagnetic iron to arsenide. So calculated electronic band structure indicates the metallicity of the iron to arsenide, and the later explain the magneto-optical properties of iron to arsenide too. And from the phonon dispersion, we can confirm the stability of atomic structure with magnetism. Lastly, magnon dispersion enables the estimation of magnetic stability, such as the magnetic phase transition temperature and the speed of the spin dynamics. But before we use the energy dispersion to analyze the magnetic phenomena, we want to confirm the feasibility of our new approach to get this magnon dispersion with the linear spin wave theory, since it is the first time we calculate the magnon dispersion of metallic antiferromagnets. In-house neutron scattering experiments can directly measure the phonon and magnon dispersion with the low energy excitation along the Q space. So with the experimental collaboration, we could get the in-house neutron scattering result of the iron to arsenide. However, it is not easy to distinguish the phonon and magnon signals in experiments because their signals are merged together. To do that in experiments, we should compare the measurement at the 2 different temperatures, one below the Néel temperature and one above the Néel temperature. Then the magnon contributions disappears above the Néel temperatures. But at this moment, simulated inelastic neutron scattering from the first principle approach can provide a practical distinction. Here is the simulated phonon contribution to the inelastic neutron scattering signals. So simulated phonon signals will predict the low energy arc shape here and the high energy crossing shapes here. And when the Q vector increased away from the origin, phonon contribution gets stronger, which is also shown in the experiments. However, this sharp signals is not explained by this simulated phonon dispersions. And this signal is identified as a magnon contribution. Simulated magnon contribution shows a unique Q dependence. Opposite to the phonons, magnon signals gets weaker with the increasing Q vectors. And this feature is also shown in experiments. So this signal is hard to be found at the Q equals 4. So in conclusions, simulated inelastic neutron scattering can contribute to identify this phonon and magnon contributions in measured signals. At the same time, the measured inelastic neutron scattering can confirm the feasibility of first principle magnon dispersion calculations too. One of the most important reasons for magnon dispersion calculation is the estimation of the speed of the dynamics, which is the connect to the magnetic device speed. So the lowest frequency of a spin wave at long wavelength limit is actually the magnon gap at the gamma point in magnon dispersions. However, the previous magnon dispersion calculation cannot provide the right magnon gap estimation because the linear spin wave theory we used does not implement the inclusion of the full-folded in-plane anisotropy energy. So instead, we used Kittel's equations to get those frequencies. So for the easy plane antiferromagnets, magnon energy states at the gamma points are split in two different frequency, alpha and beta. So they are related to that is K1 and K22 anisotropy energies, and that is chi, this is the magnetic susceptibility. So from this equation, we may realize that to obtain the faster magnetic memory device is related to the larger anisotropy energy and the smaller magnetic susceptibility. So here is some examples of the lowest spin wave frequency calculation of antiferromagnetic manganese to gold case. Manganese to gold is also have the antiferromagnetic configuration along the 110 directions. And this in experiments, the lowest spin wave frequency can be measured by the Raman spectroscopy and Brillouin light scattering methods. And from DFT calculation, we can predict that this lowest frequencies based on the calculated magnetic susceptibility and the anisotropy coefficient using the Kittel's equation, which is providing a pretty good agreement with the experiment. Some overestimation of DFT might be explained by the reduction of the anisotropy energy at the room temperature, because this anisotropy energy exponentially decrease with the temperatures. So the overall results are well matched with our expectation, which is the near the Terahertz frequency of the antiferromagnets spin dynamics too. I put one more steps on another examples with the manganese platinum. This manganese platinum is the easy access antiferromagnets. So it has only the one frequency values. And this magnon gap is measured by the inelastic neutron scattering. And the simulated DFT frequency shows a good agreement with these measured values. So this kind of the result verifies that our method can predict the speed of the magnetic memory device pretty well. And so now we move on to the excited state properties. So the first thing we check is the excited state property is the temperature dependent property of the metallic antiferromagnets. So Néel temperature is a magnetic phase transition temperature from antiferromagnetism to paramagnetism, and it indicates the thermal stability of magnetic device. So there are two different approaches to estimate the Néel temperatures. First method using the magnon dispersion, and by averaging the entire magnon dispersion energy states over the Brillouin zones with the two different averaging approximations, then we can estimate the Néel temperature roughly. So for the antiferromagnetic manganese platinum, this magnon dispersion method somewhat overestimate the Néel temperature comparing to the measured value, but it is still good enough to just roughly estimate the Néel temperature of antiferromagnets. Another method used the atomistic spin dynamics simulation based on the previously calculated exchange in coefficient and anisotropy energy by solving the model Hamiltonians. And it can estimate the Néel temperature using the sublattice magnetization and thermodynamic observables. And here I put the magnetic heat capacity. So sublattice magnetization is not sharp enough to estimate the Néel temperature due to the finite size simulation size effect. Thus, the diverging magnetic heat capacity can provide a better estimation to Néel temperatures and resulting in the close simulated values comparing to the measured value. Next, we investigate the temperature-dependent heat capacity of antiferromagnetic manganese platinum. From each quasiparticle dispersion relations using first principle method, we can calculate each quasiparticle heat capacity independently. So blank lines here shows the calculated total heat capacity, and the yellow, blue, and red lines, solid lines, shows the electron, photon, and magnon contributions. And y-intersect of the total heat capacity corresponds to the electron specific heat. And this is how the experiment is estimate the electronic contribution, which shows a good agreement with the experiment. At the low temperature range, magnon contribution is almost absent. This is because the antiferromagnetic manganese platinum has a large magnon gap and relatively low density of state at the low energy range. The phonon contributions shows the temperature cubic dependence, which shows a good agreement with the measured values. So this indicates that the heat capacity at the low temperature is mainly contributed by the electron and the phonon contribution. Lastly, we studied the impact of the external magnetic field. When we apply the magnetic field to antiferromagnets perpendicular to the Néel vector directions, all spins start to tilt it towards the field directions. So we use this behavior to develop a new method to extract the perpendicular magnetic susceptibility of antiferromagnets. So here's the procedure for the new methodologies. First, we calculate the total energy change with the moment tiltings. So here shows the figure shows the total energy change and the created net magnetization with this tilted moment. And DFT calculation only provides a discrete point. But we can use the quadratic curve fittings to get the continuously interpolated total energy curve. And then we add the Zeeman energy terms to include the impact of the external magnetic field interacting with the net magnetization. Thus, the total energy curve changes in terms of the field strength. And you may see the total energy, the change of the lowest energy points with the different external magnetic field strengths, which is the global minimum of the quadratic total energy curves. From this, we can know what is the ground state net magnetization at each field strength and resulting in the magnetic susceptibility. So by solving the total energy equation to find the minimums, we can conclude that the perpendicular magnetic susceptibility is reversely proportional to the curvature of total energy curve. So this method also can be extended to the antiferromagnets with two magnetic sets. To verify our method, we have investigated several antiferromagnetic materials, including the 6 collinear metallic antiferromagnets, 1 non-collinear metallic antiferromagnets, and 1 collinear insulating antiferromagnets. Here's the results as the calculated values and the measured values. And in general, calculated values from our new method shows a pretty good agreement with the measured magnetic susceptibilities. In details, I could find two different groups in terms of discrepancies. And group one shows a good accuracy within the 36% discrepancy, while the group two shows a slightly poor accuracies with over 50% discrepancies. Thus, we try to find the region of the discrepancies. When we check the temperature-dependent magnetic susceptibility measurement, then we could find a difference. One of the group one material, manganese difluoride, well follows the typical temperature dependence of magnetic susceptibility of antiferromagnets. This perpendicular susceptibility is almost constant, while the parallel magnetic susceptibility goes to the zero at the zero case. But one of the group two material, iron to arsenide, shows a different temperature dependent behavior. This parallel magnetic susceptibility is supposed to go to the zero, but there is unknown contributions for the surging magnetic susceptibility. So therefore, this behavior might cause relatively poor accuracies. So this might require the further investigation with the possibility of the paramagnetic defects or the site disorder in the future. So I want to conclude my talk. So we use the first principle method to quantify the exchange coefficient and the magnetocrystalline anisotropy in metallic antiferromagnets. Especially, we developed the new magnetic susceptibility calculation method and found the significance of the magnetic dipole-dipole interactions for the anisotropy energies. In addition, we extract the quasiparticle energy dispersion of metallic antiferromagnets. Magnon dispersion can allow us to estimate the speed of the magnetic device and Néel temperature. Phonon dispersion dominates the thermal property at the low temperatures, and electronic band structure confirms the metallicity of materials, and we don't have enough time to discuss our magneto-optical property today. That's all for today, and thank you for your attention. I'm happy to take any questions.
Thank you very much, Ki-sung, for this nice overview. So the floor is open for discussion and questions. So please raise your hand if you have a question. I see there's a, let me see, there's a question in the comments, but maybe you can ask the question yourself.
Okay, this question is about the exchange coefficient, and exchange calculation is calculated at the mean field level. And this is, yes, so it's not the purely the mean field levels, but we assume it is the classical method levels. So it's we assume it the magnetic moments are localized near the atomic positions, and we assume it as one of the spins. So entire magnetic systems is for the exchange interaction is described in terms of the classical level. So it used the modal Hamiltonian level. So it's for the mean field level, it's more simpler models, but it's there's an additional question. So yeah, so question is about using the magnetic force theorems. It's more like solving the spin Hamiltonian in the classical levels.
Let me just remind the participants that they can unmute themselves so they can speak instead of posing their questions all in the chat. So indeed, Ki-sung already did a good job to answer to the questions of Shublan. I don't know how to pronounce it.
And there's another one, I think.
Yes, so the other question is by Rajiv Dutt. Okay, let me just read it. What is the utility to include the Zeeman term?
Utilities for the Zeeman terms. So in this case, especially I use it for the magnetic susceptibility calculation, because the Zeeman term is the energy change with how the net magnetization interact with the external magnetic field. So by introducing this Zeeman energy term, then this total energy curve is changed in terms of the net magnetization. So with the different field strengths, these curves are keep changing, which means that this ground state under the field is also changed. So we can conclude which net magnetization is created at the certain field strength. So that's why we include the Zeeman energy terms in this calculation.
Let's first go to somebody raised their hand.
I have a.
Yeah, go ahead. Yes.
Okay. Yeah. Very nice talk. So I have a very technical question about your DFT calculations.
Yes.
So I'm more used to ferromagnetic materials. So when I first tried this antiferromagnetic material, and one of them, like you showed in your this this trend this figure, like my DFT calculation, like I always got the non-magnetic solution as my converged state. I had a very difficult time, like I still could not get the antiferromagnetic configuration as the kind of converged the state. I always get non-magnetic solution. And also I even tried, so I used the best, and I even tried this constraint, the magnetization, that option, that with the constraining direction and then moment, and then the calculation, the penalty function was still very, very high. So I wonder, what kind of method you used for your antiferromagnetic calculations?
Okay, that's an interesting question. So I wonder which material you actually studied.
We are studying manganese 2 AU gold that you showed.
Oh yeah, because if I'm not sure why it becomes a non-magnetic in your calculation, because the initial gas is the only thing affects the energy the convergence calculations. So if you choose the right initial gas of the magnetic configurations, then it should fall into the certain magnetic antiferromagnetic configuration at the end.
Yeah, so like
usually it is the the metastable structure, so it should goes to the certain magnetic configuration, I think. But I'm not sure why it becomes a non-magnetic.
So like, we start with a very standard way. Okay, we turn on spin orbit coupling, and we started with kind of quite significant magnetic moment per manganese, like 5 Bohr magnetons, or yeah.
Yeah, then I'm not really sure. Yeah.
So in your case, like so no problems. Okay.
Yeah, I didn't put any like constraint on my calculations, so it's naturally just converged to the antiferromagnetic structures. Okay. So yeah, I'm not sure what happens in your calculation. Yeah.
Thank you.
Okay, now we go to Laureen McAnulty. Okay. Can you ask your question?
Grand. Yeah, of course. Can you hear me all right?
Yeah,
I can hear you.
Yeah. Grand. Okay. Thank you, Dr. Kang. That was a very good talk. I wanted to go back again to your the calculation of the exchange interaction, the Heisenberg exchange interaction parameters. I'm wondering, in the use of J2, that's typically used to describe, at least in the materials that I'm studying, the super exchange mechanism. And I'm wondering if that's the same. And if that's the case, then what is the mediating ion?
That's like slightly different case in my case, because my material is the metallic materials, so it is not strongly have ionic interactions here. So super ionic interactions are weakly happens in during my studies, because they mostly study the metallic antiferromagnets.
Right. So, but is the J2 there? Is that referencing the super exchange, or is it?
It's not easy to say. It's a super exchange. I'd rather not to say it is the super exchange, but I haven't checked that there is a strong the super exchange happens in the metallic antiferromagnets or.
Okay, thank you. And then the second question that I had was that did you calculate it using the total energy method? that is to say that you looked at different enforceable magnetic states, and then you took the total energy difference between them in order to find these interaction parameters.
Here, I didn't use the total energy method. It's more like using the cluster method. So the cluster method is implemented by the KKR method, and I used that one. Yeah.
Okay, Grant. Thank you so much.
Mm-hmm.
Okay, there's another question by Flaviano, and then I will go back to the questions in the chat. Flaviano, can you unmute yourself and ask your question?
Can you hear me?
Yes.
Yes.
Thank you. Thank you very much for the nice talk. I have two quick questions, if you don't mind. First question is, to compute the Néel temperature, how many interactions would you include in your simulation? Something like D1, D2, D3, or a larger cluster?
So I use the interaction up to so 4 times larger than in terms of lattice parameter. So I think this is enough to include the significant exchange interactions in which can affect contributed to the Néel temperature. Okay,
thank you. The other question would be related to spin waves. You showed quickly comparison between the inelastic neutron scattering spectra and the calculated one. If you compute this and now you try to do a comparison to the experiment, do you manage from your first principles exchange to get a quantitative match for these antiferromagnets, or do you usually need to have some rescaling? How is the comparison?
We didn't use any rescaling. We just take the exchange coefficients directly from the one. We use the exchange coefficient from the first principle method, and then just solve it in terms of the spin Hamiltonians. So we didn't do any kind of rescaling in our calculation.
Okay, so would you say that in general, the agreement between experiment and these calculations is good for antiferromagnets in general?
I think in general, it shows, well, I don't have a bunch of different comparisons so far, so hard to say it is the standardly, commonly shows a good agreement, but as far as I experience, it shows a good agreement.
Yeah, that's great. Thank you so very much.
Okay, so let's go to the questions in the chat for a moment. There was a question if the magnon bands are calculated using tight binding.
Interrupt, I think.
Okay, I think my connection got interrupted. So I don't know if you answered the question then, or if you heard me. So I was going to the questions in the chat. So there was a question about the tight binding approach that was used, if it was used for the magnon bands. Did you answer to that question or?
Tight binding model. No. So here we use solving the classical spin Hamiltonian solving. So we built the spin Hamiltonians here. Let's see. So here is only part of the interactions. So it also only include the Heisenberg exchange interactions, but they also include the anisotropy energies. And by solving that too, we can extract the magnon band structure from that. So yeah, it is not the tight binding model.
Okay, then there are two quite similar questions, I think, about the localization in antiferromagnetics materials, or how the localization of magnetic orbitals is considered in the antiferromagnetic metals.
Oh yeah, so yeah, that's a good question. So it's not easy to say it's localized at a certain certain, how can I say, certain positions, but there is still some localization in near the certain atomic positions. But yeah, that's also true. There is some portions of the so-called itinerant electrons also matters on the antiferromagnetic metals. So it is carefully to interpret the phenomena if metallic antiferromagnets has itinerant electrons in the materials.
Okay, the last question for the chat, and then I go back to Ignacio, who raised his hand, is whether or not, so you did not include the Jaluzinski-Moria term. Can you please comment why you did not include it? Although Earth inversion symmetry is breaking in the system and DMI need to be included.
Yes, so we also checked the DMI interactions because the method we use is also can extract the Jaluzinski-Moria interactions. But when we check these interactions, the magnitude of this interaction is much smaller than the exchange interactions. So in this case, we ignore the DMI term.
Okay, so let's go to Ignacio, who raised his hand. So you can go ahead.
Thank you. Can you hear me okay?
Yep.
Yep.
Yeah, so my question was about localization of the charges, because it's one assumption of the effective spin Hamiltonian. So I wanted to ask you whether you studied that at the ab initio level, and also when you say considering some itinerant magnetism, does that mean that you took, for example, the magnetic moment from the bath calculation, and how is that transferred over to the spin Hamiltonian?
Can you repeat the first question? I kind of missed.
Yeah, so how did you study the charge localization at the ab initio level to validate the hypothesis of charge localization that you need for the spin Hamiltonian?
What do you mean about the charge localization?
Yes, if you studied it at the ab initio level, if you studied the charge distributions, for example, some Bader charges or something like that, or how did you consider the fact that it would be needed for the spin Hamiltonian?
I also checked the charge in our calculations, but it seems our target materials are mostly metallic materials, so there is no strong charged volume, charged density in our materials. So we think that this the impact is not that large in our materials. So we kind of like ignore the charge effect in here. And for the itinerant magnetisms, we didn't expressly include the itinerant magnetism in here because it's not easy to quantify it from the current first principle calculations. So yeah, we also kind of ignore that part.
Okay, thank you.
Thank you. I want to ask a question myself about this magnetic dipole-dipole interactions that you included. I was just wondering, since you're working with periodic boundary conditions, if there's any ambiguity in defining the magnetic dipole depending on how you choose your unit cell, as you have, for example, when you look at the electric dipole.
Oh yeah, sure. So when we see the dipole-dipole interaction equations, then this is the equation. So we can see that this is the proportional to the reversely proportional to the distance between the two different spins, magnetic moments, dipoles moments, I mean. So this is when we solve it, and this is the reversely proportional to the R cubic. So when we have a very long distance, then this interaction kind of like decays. When I create a large enough cells and then making a cutoff distance and see the energy change of magnetic dipole-dipole interactions, then we can find the kind of like convergence with the cell boundary, the distance, and we can choose the appropriate cutoff radii to get a right value of the magnetic dipole-dipole interaction here.
Okay, thank you. There's a last question in the chat, I think. Have you used one neurization after the DFT calculation?
I tried to attempt this one-year radiation after the DFT calculation, but this is it's slightly tricky because this is the metallic material. So one-year radiation is somewhat tricky part of this calculation, but to obtain the better description on the optical properties or the transport calculations, yeah. So it is still possible to do the one-year radiation in the DFT calculation for this metallic antiferromagnets. Yeah, that's true. So yeah, it is possible to do the one-year radiation to get the better description on the electronic band structures. So these days I attempt to calculate the transport property of the metallic antiferromagnets. Then I think it is necessary to include using the one-year radiation to get the better electronic band structure description.
Okay, thank you. Is there any other questions? If not, it doesn't seem to be the case. So thank you very much, Ki-sung. Thanks everybody for the discussion and the questions, and see you next time. Bye bye.